Now that we've talked about the basics of how RNNs work, let's talk about how we can actually train them effectively. So RNNs at their most basic level are very, very deep networks. In fact, a lot of the examples that I use in these slides have sequences of length, 3 to 5. In practice, we might use RNNs with sequences of length 100 or even 1,000. So at that point, they become very, very deep networks. And also the fact that the parameters are shared at different layers also makes the computation a little bit more challenging. You can kind of think of it as the parameters at the very first time step have a huge effect on downstream stuff because those effects compound, whereas the parameters at the last time step might have a comparatively lower effect, and that creates some numerical issues. So imagine that our sequence length was over 1,000. That's like backpropagating through over 1,000 layers. And we saw before that if we apply the chain rule, that's the same as just multiplying together a whole bunch of different matrices. And if we multiply many, many numbers together, if there are enough of those numbers, there are really only two things we're going to get. If the numbers are all less than 1, then we get 0. And if they're all greater than 1, then we get infinity. So we only really get reasonable answers if all the numbers we're multiplying are close to 1. And what are we multiplying? Well, we're multiplying the Jacobians of all these layers, so we want the eigenvalues of these Jacobians to be close to 1. And if they're not close to 1, then we're going to have problems. If they are low, if they're less than 1, then we get what are called vanishing gradients, which means that the magnitude of our gradient decreases exponentially with the number of layers. If they are larger than 1, then we get what's called exploding gradients. That means that the magnitude of our gradients increases exponentially with the number of layers. Why is it exponential? Well, it's because we're multiplying all these numbers together. So if we have 5 layers and they each have eigenvalues on the order of c, then that's c to the 5th in terms of the coefficient. So it's exponential in the number of steps. So we really want to get the eigenvalues of these Jacobians to be close to 1 if we can manage it. Now, exploding gradients are not too difficult to deal with because we can always clip our gradients to prevent them from exploding. The big challenge with RNNs really comes from vanishing gradients, and those are a really big problem. Now, vanishing gradients in an RNN actually have a fairly simple intuitive interpretation. Intuitively, if your gradient vanishes, that means that the gradient signal from later steps never reaches the earlier steps. So you have some loss at time step 900, and that loss has almost no effect on what the network does at time step 3. When that happens, your neural network becomes unable to maintain memory. So maybe there was something that you saw at time step 3 that is really, really important in order to get the right answer at time step 900. But if the gradient signal from time step 900 never goes all the way back to time step 3, then the network will never know that it needs to remember that thing at time step 3 so they can then use it at time step 900. And this is very bad. This prevents the RNN from basically remembering things from the very beginning. So we really, really want to solve this problem somehow. So what can we do to promote better gradient flow through an RNN? Well, the basic idea, which is similar to what we saw before, is that we would really like the gradients to be close to 1. Now, which gradient are we talking about in particular? Well, at each layer, we're going to have this operation. We're going to concatenate the previous activations. And notice here that I've replaced all the L's with T's just to keep with convention. So we're going to concatenate xt to at minus 1, apply our linear operation, and then apply our nonlinearity. And we can call this the RNN dynamics function. Let's use the letter Q to represent it. Why Q? Well, because I'm going to run out of letters pretty soon, and I need to use F for something else. So I'm going to call it Q. So this operation can say this is at is equal to q applied to at minus 1 and xt. And this is the RNN dynamics. This is basically the function that governs how the previous activations turn into the next activations. And the particular derivative that we care about when we talk about vanishing gradients is the Jacobian of the RNN dynamics, which is dq dat minus 1, the derivative of q with respect to the previous activations. And we would, if all we care about is good gradient flow, we would really like this derivative to be close to identity, or at least to have eigenvalues that are close to 1. Because if that's the case, then the gradients will neither vanish nor explode, because just multiplying a bunch of identity matrices together gives you another matrix that is identity, and multiplying together a bunch of matrices with eigenvalue 1 will give you a matrix with eigenvalues that are close to 1. So the best gradient flow would be if this Jacobian has eigenvalues of 1, or even better, if it's close to identity. Now, of course, we don't just want to force the derivative to always exactly be identity, because sometimes we do want to forget things, and sometimes we want to transform them in various interesting ways. So just forcing this to be identity is not going to work. You only want it to be close to identity when you really want to remember. So at some time steps, you really just want to say, well, at least for like the first, maybe for the coordinate 1, 7, and 8 in the activation vector, we just need to remember those. Just leave them alone, don't change them. Maybe for some of the others, you want to incorporate the new input, but for a few of them, just leave them alone, let them be, because that's how we're going to remember information from the very beginning. But you don't always want that. Sometimes you do want to modify the information in these activations, or even throw it out. Maybe once you're done using it, you don't need it for the future at all, then you want to throw it out. So don't just force us to be identity, but you would like some design where the network can decide that it wants to remember something, and when it decides it wants to remember it, then this derivative really ought to be close to identity. But other times you might want to forget, in which case you might want to set that to 0. Okay, so here's a funny design for an RNN that more or less accomplishes this. So the intuition is that you want dqi dat minus 1 comma I to be close to 0 if you choose to remember at minus 1 comma I. So I here is just the index in the vector. So at minus 1 is a vector. If you want to remember the ith entry in that vector, then you want the derivative of the dynamics for the ith entry to be close to 1. If you want to forget it, then you want it to be close to 0. So what we're going to do is we're going to design a little neural circuit for each unit that decides whether to remember or to forget. So if you're remembering, you just copy the previous activation as it is and don't change it. If you're forgetting, then you override it with something else. So we're going to have this thing that we call a cell state. And I'm going to just keep using the letter at minus 1. Sometimes people use the letter c for this. I'm going to just keep using a. And we're going to multiply the cell state, at minus 1, by some number ft, which is a number between 0 and 1. This is referred to as a forget gate. Intuitively, the reason it's called a forget gate is that if it's set to 0, then you forget what you had, and if it's set to 1, then you're going to remember it. So it's going to be a number between 0 and 1, inclusive. And then we're going to modify it, and we're going to modify it by adding something to it. So we have this modification gt, and gt is going to get added to at minus 1 after the gating. So at minus 1 gets gated, and then we add something to it. So intuitively, you can think of it like this, that if ft is close to 0, then the cell state is replaced by gt. If ft is close to 1 and gt is close to 0, then the cell state is retained. If ft is close to 1 and gt is non-zero, then the cell state is modified in an additive way. And that becomes our new cell state, at. So now the modification to at minus 1 is very structured. It's not just replaced willy-nilly by some arbitrary nonlinear operation. It's multiplied by a number between 0 and 1, and if that number is close to 1, then you remember. If it's close to 0, then you forget. And then you add something to it to modify it. Okay. Now, of course, the trick is, where do we get this ft and gt? Right? We have to get those somewhere as well. And that's where some of the more complicated design on the next slide will come in. But just to briefly summarize what happens to at, the new at is just going to be the old at minus 1 multiplied by ft plus gt. And ft is between 0 and 1, so multiplying at minus 1 by ft is basically like a softened version of a forget-remember decision. So ft can be like 0.5, but you can crudely think of it as a binary gate. It's just continuous, but you can crudely think of it as being almost binary. So then the derivative, dqi dat minus 1i, is just ft, which is a number between 0 and 1, and if we want the RNN to remember, then that number might be close to 1, and that's what we want. Okay, So where does FD and GT come from? So here I'm going to describe the full design of something called a long short-term memory cell, or LSTM cell. And you'll see in a second why it's called long short-term memory. So this design it's going to seem a little arbitrary, but there's actually a good reason for all of the pieces. So the way that we're going to decide whether to remember or to forget is based on another temporal signal, ht-1. Now, at-1 comes from the previous step. ht-1 also comes from the previous step. And you'll see where it comes from at the end. But for now, let's just say that our previous layer, our previous time step, gave us two things. It gave us at-1 and ht-1. So it's the RNN output at the previous time step. And then we have our input at this time step, xt. So that's like the new word that we have to process in a let's say, translation task. And what we're going to do with ht-1 and xt is the same thing that we did with at-1 and xt before. We're going to concatenate them. So we're going to form a new vector that has ht-1 concatenated with xt. We're going to apply a linear layer to them. And then we'll do all sorts of nonlinearities. Now, this linear layer is going to actually produce an output that is 4 times larger than the output we had before. So before, the output of the linear layer in the RNN was just the same size as ht-1. Now it's going to be 4 times larger. So the matrix has 4 times as many rows. And each of those parts is going to serve different functions. One of those parts is going to be ft, another one is going to be gt, and then we're going to have 2 other things called it and ot. So there's 4 times as many outputs. The output is 4 times larger in dimensionality than the regular naive RNN that we had before. And each of these things is themselves a vector of the same dimensionality as ht-1. So all the other operations I'm going to describe are pointwise. All the other operations are applied to every entry in those vectors. So the gating, the at-1 times ft, is pointwise. It's done for every element in those vectors. Okay, so the first thing we do is we take the ft component, the first part of the output of that linear operation, and we pass it through a sigmoid, which puts it in the range of 0 to 1. And that becomes the forget gate. So that goes in and it multiplies at-1. Then we take the second part, this is it, and we also pass it through a sigmoid, and that is called the input gate. And the input gate controls the modification to the cell state. Then we take the third part, the gt, and we pass it through some nonlinearity. And this nonlinearity is actually a choice that we can make. Conventionally, people use what's called a tanh nonlinearity, which puts it in the range of -1 to 1. Although you could also use things like ReLUs here if you want. This is kind of a design choice that's up to you. And that gives us gt. So like when I write ft bar, it bar, gt bar, that refers to the output of the linear operation, and then after the nonlinearity, they become ft, it, and gt. So gt is multiplied pointwise by it. Intuitively, it determines whether you want to have a modification of the cell state. So that's a number between 0 and 1. If you want a modification, it should be 1. If you don't want a modification, it should be 0. And gt determines what that modification will be. And this is very nice because this allows the network to independently choose whether to modify or not, and separately choose how to modify. And that turns out to be a pretty good idea. So then you multiply these two vectors together pointwise, and then you add the product to the cell state after the forget gate. And then the fourth vector, OT, that is something called the output gate. It's also passed through a sigmoid. It also goes into a range of 0 to 1. And what that's going to do is control the next hidden state. It's going to control the next HT. So what we do is we take our cell state AT, and we pass that through a nonlinearity, which could, again, be anything, but conventionally we would use a tanh, although we could also use a ReLU. We pointwise multiply it by OT, which essentially gates it. So if OT is 0, then there is no output. If OT is 1, then the output is preserved. And that becomes the new HT. And this new HT is also what we use if we want an output at that time step. So if we want some kind of readout function, some kind of decoder, HT is what we would use. So this might seem like a somewhat complex design, but one way you can get some intuition for what's going on here is we're trying to preserve the role of AT as a mostly linear signal. So we actually don't apply any nonlinearities to AT. All of the operations applied to AT are linear. It's either multiplied by a number between 0 and 1, or it gets something added to it, or both. All the nonlinearities are applied to the H's. And as a result, the gradients on AT are going to be pretty simple. So the derivative of AT with respect to AT minus 1 is just going to be FT, and FT is directly determined at that layer. So not having any nonlinear functions affecting AT makes its derivatives very well behaved. At the same time, we still retain the benefit of nonlinearity by having a nonlinear modification through GT and a nonlinear readout through HT. Now, you might say at this point, isn't this all a little bit arbitrary? Like it's like this crazy circuit that we just kind of made up. And the answer is yes, but it ends up actually working very well in practice, much better than a naive RNN, because the derivatives of AT with respect to AT minus 1 are so well behaved. Now, some of the choices here are a little arbitrary. Like, for example, do we really need the output gate? Do we really need the input gate? Like, maybe we could just get away with FT and GT and not bother with the other parts. And you can actually simplify the basic LSTM cell in various ways that I'll talk about shortly, and it can work almost as well in that case. But this is kind of the classic LSTM cell, and this is the one that most people end up using. So why do these LSTM cells actually work better? Well, the simplest reason is that AT is modified in a very simple way at each step. It changes very little, and how much it changes is determined entirely by FT. Now, you might complain that before I said that we really want the derivatives to be 1, and FT is definitely not 1. It's a number between 0 and 1. In fact, usually it's going to be less than 1. But that still ends up being good enough in many cases. So you can think of AT as essentially the long-term memory. The HT, the other part of the recurrent state, changes all the time. You can see that HT is essentially overwritten by the linear operation, W. So this is kind of the short-term memory. HT performs much more complicated nonlinear processing, but it's very bad at retaining things over long spans of time. AT has comparatively much simpler linear processing, but it retains information over long time periods. All right, some practical notes about this stuff. In practice, RNNs almost always have both an input and an output at each step. And we'll see why this is so important in the next section. In practice, naive RNNs, like the ones in part 1, almost never work. In practice, if you want an RNN, you will probably be using something like an LSTM cell. Now, LSTM cells work okay. They're kind of complicated, they're a little bit arbitrary, but they're dramatically better than naive RNNs. So if you just want some default go-to thing to get your RNN to work, probably using an LSTM cell is what you want to do. Now, they still require more hyperparameter tuning than standard fully connected or convolutional networks. You want to be careful with things like gradient clipping, learning rates, and so on, and they're usually a bit harder to choose than they are for standard naive neural networks. There are also some alternatives to RNNs for processing sequences that can work a lot better in practice, and we'll learn about them later. These are things like temporal convolutions and transformers, which are temporal attention models. So we'll learn about those later. LSTM cells are also annoyingly complicated, but once you implement them, they can be used the same as any other type of layer. So typically, to get rid of all that complexity in an LSTM cell, you would just code up a piece of code that abstracts away the LSTM as just another layer, and then you just use that layer the same way that you would use a convolutional layer or a linear layer. So basically, this is the beauty of abstraction. Once you abstract them away into a function, you kind of don't care how complicated it is. But if the arbitrariness and complexity of the LSTM cell is bothering you, there are some variants of the LSTM that are a bit simpler and work just as well. For example, one very popular variant is something called a gated recurrent unit. A gated recurrent unit is basically like an LSTM, but without an output gate. So without an output gate, ht is always set to be some nonlinearity like a tan h applied to at. And that tends to work pretty much just as well. In fact, the reason that GRUs are a bit less popular than LSTMs is largely due to historical reasons. GRUs are a bit more recent. You could imagine that you could modify the LSTM in other ways. The really important part of the LSTM is basically the forget gate. The input gate could also be removed potentially. In some experiments, that seems to work a little bit worse, but it's a very reasonable choice. And if you remove the input gate and the output gate, then you really only have 2 times the number of outputs and 2 times the state.